right, let's look at definition of a derivative at a point. So we're going to start calculus, the real meat of it. So if I have a function f of x, and I label two x values, let me label these 2 points here and here as ordered pairs. So this guy at c would be, the x value is c, so the y value would be f of c. And likewise, if this x value is x, then the y value would be f of x. And so let me connect those with a line, and that would be a secant line. So if I drew that secant line and ask you to find the slope of the secant line, well, what do you remember from, when you first started algebra? Slope is the change of y over the change of x. In other words, subtract the y's over subtract the x's. So you can subtract either way, but let's do x minus c. And if I did that, I would have f of x minus f of c over x minus c. That would be the slope of the secant line. And that, in fact, this piece right here is called the difference quotient. Difference, of course, meaning subtract. Quotient meaning divide. So that is the difference quotient. So you'll see that, and a lot. You'll hear me refer to the difference quotient. Okay, so what does that do for me? Okay, that gives me the slope of that secant line. Well, my question is, what a derivative at a point is if I drew this tangent line, so the red one is the tangent line at C. Is the green line the same slope as the red line? Well, clearly you'd say no, it's not. But what could I do to make it closer? I mean, the green line would be an approximation for the red line, but it certainly could get better. What could I do to make it better? And hopefully you would say, well, instead of having the dots so far apart, like if I could move x right here, and I did the secant line through those 2 points, look at the yellow line and the red line. Certainly a better estimation, the yellow one is, than the green one. So what could I do to make the approximation better? I think you can see that the secant line gets closer and closer to the tangent line as x is getting closer and closer to c. So if I move this x over, the secant line gets closer to the tangent line. So the secant line gets closer to tangent line, as x gets closer to c. So what could I do? I'm like, okay, well, the yellow line is better. What could I do to make it even better? You'd say, well, move it closer. So move x to about right here. Well, if that's good enough, why not move it here and here and here and here? Or in other words, take the ding, ding, ding. What have we done all last unit? Take the limit. If I take the limit as x approaches c of this difference quotient, that's not going to give me an approximation. That's going to give me the derivative at a point. And that, my friends, is the definition of a derivative at a point. It's going to give, if I take the limit as x approaches c of that difference quotient, it's not going to give me an approximation. No, 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 no. It gives me the exact slope of that red line. And that's what a derivative is. So this is the notation for the derivative at x equals c. And this, which is the slope of the tangent line at c. So if someone says, hey, you're in calculus, this happens all the time. You're in calculus. Tell me what a derivative is. you can say, you know, that the derivative is the slope of the tangent line at x equals c. So we're going to use that definition of derivative to find particular values. So let's look at this first example. Use the definition of derivative to find the value of f prime of c when c is 5 and f of x is that function. Of course, I could have written this a different way. I could have said, find f prime at 5. That's really what that first sentence is saying, if f of x is that function. Well, I want you to fill the, if it says using the definition of derivative, your first line, kind of like the definition of continuity, if you want to write this original template down, that's fine. But I want it specific to the problem. So f prime of 5 is going to be the limit as x approaches 5 of f of x. Now what is f of x? This is f of x. So I have x squared minus 8x plus 18 minus f of 5 all over x minus 5. Now this f of 5, I'll be honest, when I'm doing this problem, I kind of do that out to the side. I kind of over here, or even maybe first, I go, what is f of 5? And I do that in my head just to kind of keep it straight. And so let's see what f of 5 is. That'd be what? 25 minus 40 plus 18. So if I do that math, that would be 3. So I'm going to plug that in because it's f of x minus f of 5 all over x minus 5. Now let's clean him up and let's use our wonderful notation that we learned from last unit. We have x squared minus 8x plus 15 all over x minus 5. Now you can, of course, try direct sub, but what's going to happen? You kind of look at that bottom and probably know that, oh, I bet you I get 0 over 0, which I do. And we know from last unit as well that when that happens and I have polynomials, gosh, this almost sounds like something I could have done last unit. I would factor, and what do I get? Well, the 5x minus 5's cancel, so I take the limit as x approaches 5 of x minus 3, and we know that is 2. So what do we get? What do I want you to write your answer? I want you to write f prime of 5 equals 2. And you're going, that is awesome. I am so excited I can find a derivative. But you're thinking, what the heck does that even mean? I want you to know what it means. It's great to get the answer, but you also need to understand what it means. And what it means is simply this. If I were to draw this function, okay, and I'm not drawing an accurate 2-scale drawing of this function, so don't quote me on that, but it's going to do something, whatever, like this, whatever. Okay, where this is going to be 3 and this is going to be 5. But actually, well, not necessarily. Sorry, that's not 3 and 5. Wherever that is, okay? I'd have to factor that and see what it is, but it's something weird. But it's going to be an up parabola and et cetera, et cetera. What I'm saying, wherever this is, 1, 2, 3. I hate to put markers on there because that's not an accurate graph. But what I'm saying at x equals 5. The slope of the tangent line at 5, the slope of that line is 2. Now I can't really see exactly where that, if that's right, unless I drew an accurate graph, but I certainly can see that it's positive. I mean, think about this. If I would have done the slope maybe over here, okay, the slope over there, if I did the slope at 1, the slope at 1 is going to be negative because look how it's drawn. So that's what it means. When you're finding the slope of the tangent line, that is what you are finding. When you're finding the derivative, you're finding the slope of the tangent line at that point. Okay? Let's look at, let you try the next. What did I just hit? So it says, let's find the slope of the tangent line when x equals 4. So let's write down the kind of the model here. F prime of 4 is going to be the limit. Please don't forget to write the word limit as x goes to c of f of x minus f of 4 all over x minus 4. Now let me get specifically what those things are. So let me go ahead and get f of 4. What is f of 4? 16 minus 12 minus 4. Oh, that happens to be 0. Okay, so f prime of 4 is going to be the limit as x goes to 4 of f of x. Putting minus 0 is kind of silly over x minus 4. I'm going to do a factoring. Over x minus 4. Those cancel. I can take the limit and I get 5. So what did I just figure out? I figured out that the derivative at 4 is equal to 5. That's what I figured out. So as you can see, once again, it goes back to things that we did last unit. So if you had a hard time with the limits from last unit and you missed those, guys, it's gonna bite you again. You have to be able to recall the information. You've got to learn this stuff the first time through, and you can't just, oh, test is over, so I'm going to forget it. It doesn't work like that in calculus. You have to remember and hold on to information. So let's look at this last one. The last one is you're not really calculating things, but it's just getting you very clear about really what does it mean with tangent lines, etc., like just to compare them and look at them and understand what that is. So if I ask you, letter A says draw tangent lines at the indicated points. So I can just draw, that would be the tangent line at A. Here's B, there's C, D, E, and F. So those are the tangent lines at those specific points. Letter B says, at which point or points is the derivative equal to 0? Well, think about what that means. The slope of the tangent line is 0. Well, what kind of line has a slope of 0? Oh, a horizontal one. So look at the lines that you just drew. At what points did you draw horizontal lines? Well, you did that at B, D, and E. At what point or points is the derivative less than 0? Where is the slope negative? Well, that was point. This guy right here would have a negative slope. That's point A. And finally, at which points is the derivative positive? Well, that's positive slopes are like this, so that's C and F. And that's what you'll be doing on the homework. You'll be doing some definition of derivative at a point, and then just some comparing and some questioning of tangent lines. I will give you a hint on one of your questions on your homework. I won't tell you which one, but if you have something that you really can't see the factoring, you may have to do long division. Oh my. You may have to do long division on a problem. So I'll give you that hint as you do your homework. All right, good luck.